Sweet. All right, let me see who's here. 2, 2, 3, 3. Yay, sweet. Okay, cool. Welcome. Happy Monday. Good to see you. How was your weekend? All good? Snowy? Inside times? Yeah. Anybody play in the snow? Yeah, nice. I played in the snow. It was so nice. It was perfect. And where did you drive around? My friend's neighborhood. It was really fun. That sounds fun. Don't try that at home, kids. Okay, that's the safety part now. I'm legally not obliged. That sounds awesome. I want to do it. Okay, cool. That sounds cool. Crazy. Yeah, that snow was really nice. I liked that. It was such a cool surprise. The snowflakes are huge. They were monsters. I love the snow. I miss snowboarding. I haven't been in like 2 years. Kids. Have kids, they said. It'll be fun. They are awesome. So that's what I did, hung out with the kids. Questions at all on like this weekend's, or if you finished it last week's stuff, anything you want to talk about? I'm going to put up the solutions. I don't think I've done that yet. I wanted to wait until after the debate, of course. But I'll put those up so you can check them yourself, and then happy to go over them. We'll have lots of downtime this week to practice and ask questions and do your own thing. I'm really hoping that I can get you away from the screen, you guys in front of me, Tuesday and Thursday a little bit. Folks at home, Wednesday for sure. So you can just practice on your own as you feel like it, whenever you want. But of course, you can always come and I'll work through stuff as we prepare for Friday's test at home. I'm going to get a review out to you tomorrow. That's the plan. I'm going to write it tonight. Haven't written it yet. Yikes. Write it tonight and get it out to you as soon as I can so we have lots to practice with. But if you're good from the last homework, or at least you'll wait until you see the solutions to ask questions, that's fine too. Then let's do our last lesson of chapter 1. Amazing. Okay, and that happens on page 57. We just ended on page 56. Let's go to page 57. And make sure we're cool. Okay, and if you look at the top, you'll see what the I just tried to scroll on there. Okay, there we go. Limit-based continuity. Okay, remember, this chapter is entitled Limits and Continuity. And the goal eventually was to reach this page. So we can formalize it, put it together. You're going to see that at this point, it is very intuitive. You're like, oh, yeah, that makes perfect sense. Duh, awesome. We just make it formal, okay? And we actually go about the process a little more formally, but not super formal, but not super crazy. So eventually, we will fill in these 3 boxes of the 3 things that must be true if we want a function to be continuous at a point. Okay, but we can't fill those in yet until we kind of explore the table below that, okay? And that's the plan. We're going to use this graph right here. That's g of x, all crazy. Can't imagine what that function looks like. And we're going to look at some spots along the way. Now, I want to be able to see it with you as much as I can. So I can go to like there. I can show you the first 4 while still looking at the graph. But the last 2, I'll have to scroll. But let's just use the graph. You see, like x equals a. Okay, there are some values. And then they say, let's go to a from the left, a from the right. Okay, what's blah, blah, blah. We'll just kind of fill out each column of this table, leading to the decision. Is it continuous at that point? Okay, the answer will be yes or no. And then we will take a look at the ones that did versus the ones that didn't have continuity there. And we'll jump to some conclusions. You're going to be 100% right. It's going to be easy, I think, once you get there. And then we'll turn to the next page and we'll practice it. And yeah, chapter 1 will be done. So we'll probably actually end a little early, and we will have time to jump into the multiple choice practice that exists on the pages after that. Cool. So let's do it. Take a look at the graph. They called that g of x. I don't know why they capitalize the function sometimes and not others, but they did on this one. And so they're stopping us at 1, 2, 3, 4, like 5, 6 points down here. But let's just look at the first one. X equals, I'd like to see where we're at. There we go. -6. First question is the function defined there? At x equals -6, is there a point on that graph that is -6 comma something? No. So what should we say in that spot if the function doesn't have a point? It is undefined. You can write the whole word or the first 5 letters with a period after. If you want to abbreviate, that's fine. I usually like it. And that was really the only question that had to do with the actual function itself, right? Is it defined there? The rest of these all have to do with limits. And the first one is limit from the left. And they said as x approaches a from the left, okay, so that's a in this case, so -6. All right, so let's go from the left. What y value are we getting close to? If we are getting close to anything? 5. Yeah, right? Because follow the function from the left, and it looks like we're headed right towards that spot. Right towards that hole that kind of led you to the first answer of undefined. It gives us an actual limit, so that's good. What about from the right? What y value getting closer as we follow the function from the right? Also 5, sweet. So what's the limit of g of x as x approaches -6? Still 5, because these are the same, sweet. But with this last question, would you say that the function is continuous at that point? Knowing what you know about all the things kind of leading up to it, the fact that it's undefined there, but that the limit from the left and the right are the same, the limit exists. Would you say it's continuous? And I would agree with you. I don't think so either. And in my mind, when I think about continuity, in my mind, I kind of change it to the word connected. Continuous, connected. Continuous, connected. Like, can I, trace the graph in the space nearby and not have to lift up my pencil to do it, right? So okay, a couple boxes to the left, I go like this, go like this, go like this. But I get to here, I have to lift and then place it somewhere else to be able to keep going, right? And that lift and replace makes me feel like things are not continuous, they're discontinuous at that time. Sweet, okay. Yay, done. Next one. Little exploration, and then we come to some conclusions. All right, -3. All right, that's the x value wants to go to. Okay, is the function defined? And if so, what is its value? Is there a point when x equals -3? Where is it? 2. Okay. What's the limit from the left, right? That little negative says go from the left, couple boxes, track yourself along the function. What y value are we getting close to? Good, sounds good. But what about from the right? Function's not up here, it's down here. What y value are you getting closer and closer to as we head towards -3? -4. So if the limit from the left is 2, but the limit from the right is -4, what would you say about the limit? Does not exist. C and E. Right? I want these two to be the same if I want to have a limit. So what do you think? Continuous or not? No way, right? Huge gap there. That's not even a removable discontinuity. There's a big, huge space right there. No way. Got to lift my pencils, move it somewhere else in order to go through it. And so I know it says g of x being continuous at x equals a, but in my mind, it's like the space around, like a super small space around it too, because I want the limit to exist if we're talking about being continuous, right? For sure. Cool. All right, next one. X equals 0. Let's get rid of this. Let's go towards 0. Okay, so is there a point there? I know it's not like super huge and circled in, so don't let that bother you. When x is 0, where is the point? -1. Good. I know it's not some big circled in point. That's because they don't need to do that because it's not something weird, right? It's not some hole with a point somewhere else or something else going on. So definitely -1. Take limit from the left. Same, right? Yeah, cool. Sweet. Head towards that same spot. What about from the right? Awesome. So what's the limit? Awesome. So what do you think? Does it look continuous in that space? Absolutely. I can very easily connect the graph, like a box or two to the left and a box or two to the right. When I say that, that's a good visual, but it could be way, way, way smaller than that, and it could still be. We love continuous. Makes the rest of calculus work. Okay. Sweet. 0 is good. We like 0. Okay, let's go to 2. X equals 2. Is the function defined? No way. Got an asterisks up there, right? And so I'm still going to say undefined. I don't have to describe necessarily what's happening there. It's just whether or not there's a point. Cool. Limit from the left. Okay, so kind of tracing a couple boxes to the left. Now, because the one-sided limit as we approach an asymptote, we have a little freedom here to say one of two things. What's going to tell the best story from the left-hand side? Infinity. Now, does not exist? Absolutely. You are all good to say does not exist in that spot as well. That's cool. Infinity is great. One-sided limits only, though. What about from the right? Again, does not exist. Awesome. No problem. But if you want to put the infinity and negative infinity because they're one-sided, for sure. But this is not one-sided. Okay, this is as x approaches a. So we have one and only one choice in this spot. That has to be does not. Okay, you cannot, even if they were both headed towards infinity or both headed towards negative infinity, the limit is a real number. And so I have to say it does not exist in that spot. What do you think? Continuous or not? Discontinuous. Undefined and the limit doesn't exist. That is a bad recipe for some continuity. Sweet. So those are the first 4. I'm going to have to scroll and erase. And I'm probably going to lose most of the graph to do that. But you've got the graph in front of you here on page 57. So away I go. 6 and 8 are our last 2. Let me get my piece of paper so I can look at it. Is the function defined in that spot? We have a point for mine? Where is it? Where are we at? X equals 6. Yeah, there's a point there at 1. Good. Sweet. What is that limit from the left? That's our first question, right? Yeah, for next one. Where are we headed as we trace the function along the left-hand side? Going up towards 4. Good. But what about the limit from the right? -2. And I know that there's like some weird stuff happening there at 8 too, so you don't have to go very far to get yourself a sense for what's y value we're approaching. It looks like -2. That's good. What do you think? Limit from the left is 4. Limit from the right is -2. So what would you say about the limit itself? Does not. Does not. And based on a very informal understanding of continuity, what do you think? No, I can't. Graph is not connected there. And so in your mind, continuous connected, a really good kind of mindset there. Yay, last one. Hello, Joe. Number 8, point defined. Do we have a point at x equals 8? Yeah, down at -4. Not at the whole. That's okay. We do have a point there, so that's good. Limit from the left. Limit from the right. So what's the limit? Awesome. So nice. Like there's numbers everywhere. I think maybe for even the first time. I guess maybe at -3 we had numbers everywhere, but we didn't have a limit, right? Now they're all there, but does it look continuous? There was the best. The one and only spot, I gotta scroll again. The one and only spot on this graph where we said we believed that it was continuous. And so what we're going to try to do now is use not just the results at 0, but also the results everywhere else to come up with 3 basic statements that have to be true in order for the function to be continuous at that point. And again, it's only at a point. And I know we say add x equals a. It's obviously the space kind of nearby as well. But not the whole function. We're just looking at a very specific point. So, go ahead. One thing that you think needs to be true, and go in whatever order you think makes sense. There really is no specific order. Got to be defined. We have to have a point there. So I'm going to say, let's see, they called it g of x, right? So I'm going to say g of, now it's a specific point, like g of a. We're saying, you know, the function is continuous at some x equals a. That is defined. Okay, gotta be defined. If there's a gap there, hole there, ask them, so not going to be continuous. Okay, what else? What else needs to be true, do you think, for the function to be continuous? Yeah. So we have to approach some, or you're jumping ahead a little bit. Let's have a limit to start. We have to have some kind of limit, right? At that exact same point. So let's say, I don't know, like the limit from the left and from the right. So we can just say the limit as x approaches a of g of x, it has to at least exist. They're kind of not being too specific about comparing the first part, function having an actual point there. And the second part, kind of getting to the calculus where the limit exists. But now, let's make them the same. Because if one of them is defined and the other one exists, well, we saw, I forget which one it was, right? That last one, x equals 8. Once it was defined, the limit existed, they just happen to be different. We want them to be the same. And so what we're going to do, this again, it doesn't matter what order you write it in, but I want g of a to equal the limit of g of x as x approaches. And so, like, I think these two can flip-flop. Like, it doesn't matter what order you decide you want to do them. And this is the order that we'll do them in, because that's the order you guys picked. That's cool with me. Period 2 did it the other way. They said, oh, the limit has to exist, function has to be defined, and they have to be the same. But that's it. And that makes so much sense, right? It just feels so natural and intuitive, like, oh, I want to be continuous. Well, I better just, like, cut right through that point as I go. But we just kind of get a little bit formal with the way that we do it. We actually like check number 1, and then we check number 2, and then we check number 3, and then we'll like jump to a conclusion. We'll say, oh, therefore it is continuous or it's not. And that's what the second page gets us to practice. So go ahead and turn the page to 58. Let me see if I can back up a little bit. There. So I can write and see at the same time. Okay. Now, if number 1 works, it is defined, yay, we'll move on, and we'll go to number 2. If number 2 works, yay, it works, we'll move on, and we'll try number 3, and we'll compare them. And if all 3 of those things work out, then it's continuous. But if at any point along the way, like if the function is not defined, stop. Jump right to the end and say it's not continuous, right? If the function is defined, but the limit doesn't exist, stop right there. Jump right to the end and say, no good, the limit does not exist, so my function cannot be continuous. So all 3 of those things have to be true. So if one of them fails, the whole thing falls apart. Okay, cool. So let's do it. I'm just going to, I'm going to put like one, here's the first thing we're going to do. This is not number 1. This is the first part of that. I'm just going to go by your list that you guys just made at the top. Let's figure out, they called this one g of x again. So I'm going to say, okay, g of -8. Why -8? Because that's the number they give me. And I want to see what that is. Let's actually define it. I'm not just going to say it's defined. I want to know what it is. And this is also good practice with graphs and stuff too. Why not? Cool. So what is g of -8? Yay, it's defined. There's a number. I'm happy. I'm ready to move on. And although, gosh, you look at that and you're like, duh, Rosie, that is not continuous. Why are you making me do all this? So we get used to a very specific process in calculus that you have to build on ideas as you go. Because maybe we don't have this graph to look at, right? You got to be careful jumping to too much conclusions. But I mean, look at that. There's a hole there, not going to be continuous. Let's prove by doing this. The next thing we were supposed to check is the limit. As x approaches whatever that x value was, they gave it to us, it was negative b. What's that limit? Negative 5. Good, right? From the left and from the right, we are approaching the hole down there at negative 5. Okay, so now number 3, we compare that. So I'm going to say, okay, like g of negative 8 on the left. I'm going to leave a little space here just for a second. I'm going to compare that to the limit of g of x as x approaches negative 8. And we're going to make a statement about their equality. Are they the same? Duh, no. One's a 4, one's a negative 5. Here's the statement. These two are not equal. Got a little exaggerated with that slash. Then we make a conclusion. What are those 3 dots? Therefore. Okay. We looked at 3 things. Yay, it was defined. I'm going to keep going. Yay, the limit exists. I'm going to keep going so that I can compare the 2. But now I can say with confidence that because this third one fell apart, therefore g of x is not continuous. That's 2 words, or you can use 1 word, discontinuous. The word not continuous, the word not continuous, or the word discontinuous, but say where, at. You can even use the at symbol, that's cool, or you can write the word at, okay, at x equals negative 8. That's my conclusion. That's what this is all building towards. The question is whether or not things are discontinuous or if they're continuous. So if I'm circling anything, I'm circling that. Came to that conclusion pretty logically, right? And very simple logical steps. Oh, see if there's a point. See what the limit is. Compare them. They're all the same? Cool, it's continuous. Are they different or does something fall apart? Then it's not. That's it. Very simple last idea. But a very important one. Continuity is crucial for us. You're going to see that as we go. Okay, cool. Number 2. Let's do this one, and then I'll let you do number 4. I'm going to just write it up here so I have some space. So this is the first thing I want to check. I want to check g of negative 6. I want to figure out what that is. Maybe I have a graph, maybe I have a table, maybe I have an equation. The process is the same, doesn't matter. I got to peek here because I'm covering it up. What is g of negative 6? I know there's no like big circled in point there. That's actually a good thing. We like that. What is that y value down there? Negative 7. It's there. Cool. First part done. Now I check the limit at that exact same spot as x approaches negative 6. Let's see what we get. Well, from the left, from the right, what y value are we getting close to? Negative 7. Now, we're formal enough to write out the comparison. These two are equal. Duh, I know, you just wrote that down. They're literally right staring in front of you. But writing that allows us to now jump to the conclusion. And I'm not jumping very far because I took my time and I wrote it all out. Looks good. G of x is continuous. Why? Because this exists, this is defined, this exists, and there's g of x is continuous. At, tell me where, x equals negative 6. the idea. It's pretty simple. You have to know how to read your graphs well. But knowing like step 1, step 2, step 3, conclusion. Okay. Now on Friday, when this kind of question comes up, you will have these notes to look back at. So you're not leaving something out or writing something that you don't have to, or misrepresenting something, or saying the wrong thing, or leaving out the at x equals part, because I hate people lose points on simple kinds of questions. All right, so this is number 1, this is number 2. All right, you try number 3. See what you can do. See if you can prove one way or the other whether the function is continuous at x equals 4. I'll give you a chance to try it on your own, and then we'll do it. Well, I'm going to do like 1, 2, 3, potentially, and then kind of how this is going to play out. Here we go, -4. I don't even need to do part 3 if part 2 falls apart. Save yourself the trouble. And let's say you did that in the other order, like I did with second period. The first thing we did was check the limit. We saw that the limit didn't exist, straight to the end. Skip 2, skip 3. If one thing falls apart, then you can jump right to the end and say, definitely, this thing cannot be continuous if there's no limit. Or it's not continuous if there's no point. Or it's not continuous if those are different. But if all 3 work out, then yay, we're good. That's it. Chapter 1. Done. Did it. So excited. Yay. Now, what I want to do, of course, with our last 20 minutes, we'll keep practicing. We have that last page front and back. I'm going to keep working on that. But let me tell you a little bit about how I want this week to look and feel for you. First, we'll start with those last 2 pages. Now, look at those last 2 page numbers. We just finished page 58. This jumped to page 76. Okay, that means, and I'm doing this intentionally, is that I am leaving off some sections. Okay. Now, I'm happy to go through this with you. For those of us that want a little bit deeper of an experience when it comes to calculus, but I mapped out what it's going to take to us to get to May and get where I want to be, especially those of us taking the college trig See Succeed file and want some practice with that before we get to that. I had to skip some things along the way. Okay, it's just the nature of starting calculus in February and not January. So there's some practice with some piecewise, and then there's just more of this kind of practice. I will include this page as part of your review so that you can get a little bit better with that section once I give it to you. There's an entire section that recounts the intermediate value theorem. Remember, I drew up on the board, you stop at that red light out there, and you go 3 miles down the road, and now all of a sudden you're going 50, right? Were you definitely going 25? Were you definitely going 35? Were you definitely going 49? Were you definitely going 51? Maybe, maybe not. All right, that's what the intermediate value theorem does, and it just kind of gets limits talking about that going on. Really, it's about if the function is continuous, yes, all those limits are good. Function is not, everything breaks it down. Okay, so I'm skipping all that. So what two conditions must be true to verify the applicability? The function must be continuous everywhere on that interval, everywhere, from like A to B, all the way through, okay? And we need different y values, right? When I said here, you stopped at 0 and then you stop at the next red light, were you definitely going 5 miles an hour? Maybe, maybe not, right? You could have been going 1 mile an hour, you could have been crawling, okay? But I didn't think it was worth doing that all over again. Then they talk about the difference between infinite limits, so whose answers, like the x as we go to infinity or x as we go to negative infinity, versus limits at infinity, whose answers give us that. All good. It's just looking at a graph and giving answers. Here's the last thing, okay? And I'm not going to spend a ton of time talking about it, but I do want you to just see it, but I promise it will not be on the test, just so you're familiar with it. I'm happy to print this out for you in case you want to try it. Check out this rational function. What is the degree on top? 1, right? The largest exponent is a 1. But look at the degree on the bottom. What's the square root of x squared? So what's the degree of x? So 1 over 1, right? And when your degrees are the same, when we talk about n behavior, we should be just approaching the ratio of leading coefficients. We think back to like honors free calc chapter 2 in rational functions. But think about what happens as x goes towards positive infinity. Okay, cool. Like that's going to be positive, some super positive number, and that will also be positive. But taking a positive number, squaring it, adding 1, and then taking the square root, that's all got to be positive. And so I can head to the ratio of positive 2 over positive 1. So as I head towards positive infinity, there I am headed towards 2. Okay? But look at what happens when we go towards negative. What's the sign of the numerator going to be? Really big negative number in there for x. Got to be negative, right? 2 times something negative minus 2, super, super negative. So the top's going to be negative, but look at the denominator. Take a negative number, square it, add 1, then take the square root of that. That's got to be positive. So when you go towards positive infinity, it's positive. But when you go towards negative infinity, you have a negative over a positive, and we end up heading towards negative 2 instead. And so there are rational functions that have not 1, but 2 horizontal asymptotes for 2 different n behaviors because of that square root of the x squared, messing things up, okay? And it's just kind of cool and interesting to look at what could happen. That's all you do. You think about, okay, am I going towards positive infinity? And what would happen top versus bottom versus going towards negative? Again, I had to keep some stuff out in order to get us to the point where we could finish chapter 1 in February. So just more practice like that. Then the homework that goes with it, according to them. And then we get to page 70, whatever, 76. Okay? And this is where I want you to start. Okay? With our last 15 minutes today, and folks at home, you guys can stick around and watch some of this work out, or you are good to go, and I will see you in person or virtually tomorrow if you're for virtual. I will have a copy of, hopefully, the review for you guys in person tomorrow. And then you guys that are sitting in front of me right now, hopefully, I can get a digital copy to you tomorrow that you can work on at your leisure. And then I will have a physical one for you on Wednesday. Now, for cohort A, you guys, I want to start giving you this week a bit of a break from having to be stuck in front of your computer all the time. So tomorrow and Thursday, you guys log on for attendance, you stick around as long as you want, or as short as you want. Okay. The more you stick around, the more you'll see me and hear me talk through examples. And so take that as much as you want, or you can always go back and watch the videos. But I want to give you a little bit of a break because once we get to chapter 2, it is go, 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 go. We're going to be back on every day. So I want to give you this week as a little bit of a buffer, and then also maybe give you some time to do some other things. Right? You have lots of other classes besides calculus. You have other things to focus on, so I want to give you time to do that. Okay. So folks at home, take off if you want, or you can watch me basically work through the first page for those that want to see it. I won't talk through anything unless you want. But before you go, there are a couple that I want you to first know it is okay to skip. Okay? Turn to the very back of that last page. Take a look at number 8. There it is, right? There's that x over square root of x squared kind of question. Feel free to skip that one entirely if you want. I'm going to do it now that I've talked about it. You have a limited understanding of how it works. But I will not put a question like that on the final, I promise. Or the final, chapter 1. Or the final, for sure. Okay. Now, some ones that we haven't talked a lot about. So you can feel pretty good about not having to do a question like this on the test, but maybe something that we're a little bit more familiar with that would just be good practice for those of you that want to. So you can definitely skip number 8, but these you can put a little star next to do or not. Okay, I will do all of them, but don't feel like you have to do these to be able to be ready to go. Starting with number 4. Okay, the piecewise one. If you want, great. It's a great question. It's the kind of thing you want to build towards if you're going to BC. Great. If you're taking A/B, you'll do it again next year, for sure. Okay. Number 5 as well. If you want to star that one, that's okay. That's that limit at infinity that I was talking about. It's really just going to go to like a pre-calculus mindset. It's a rational function. I'm just going to compare degrees top and bottom and think about m behavior. That's all I'm going to do there, but that's not really something we've spent a lot of time on, so that's okay. And then turn the page and star number 7 as well. Okay, number 7. So again, you can star 4, you can star 5. We're definitely going to do 6 for sure. You can star number 7. Okay. Number 7 gives us a function and asks us to evaluate the limit of the difference quotient. Okay, that is day 1 of chapter 2. That's how things are going to start in chapter 2, more or less. So I'm not going to put that on the chapter 1 exam. But they did give us a question like that, not on homework 1.5, but on homework 1.4 that I said it was okay to do your best, right? To let h go to 0 and like x was still part of the answer. But we haven't like started that from the beginning, like a question like this. So do not worry about number 7. I'm going to do it on the solutions once I do it, but I will not put something like that on. Okay. And then skip 8, like I said, 9 is good, 10 is good. Okay. Those are just good ones. Again, like you see 10 is piecewise. Yeah, maybe start if you want, but I think it's a good one to get. Okay. So today, with this our last 10 minutes, you can start working on 76 and 77. And I'm happy to talk through any of them with you. For example, I know I talked through number 3 during second period because somebody just wanted help factoring the numerator there for number 3, right? With that x cubed minus 8, just that difference of cubes. They just wanted to see that one more time. And somebody was just thrown off by number 1 because they tried factoring and dividing and doing all sorts of crazy stuff when in reality, all you have to do is plug it. Okay, so I'm going to circle the answers for these, so don't peek until you're ready. But if you want to see any of them worked out, of course, I will definitely post these solutions for you. You do not have to submit this. You do not have to submit this. Okay, you do not have to submit anything this week except for the test on Friday. Okay, so do as much or as little of the review as you need. But if you don't do the review and your test reflects that, that's obviously an easy connection to make, you want, like I want to do. Let's just do it. Yeah. So I'm here. Just ask questions if you have any, or take your last 10 minutes. Just get started. I am moving on to the second page. Okay. Sure.
Thank you, Rosie.
You're welcome. Have a good day. See you tomorrow. Mhm. Mhm.
So, this one,
Mhm.
doesn't exist. So, is that statement even valid? Like, 'cause it doesn't. It's
So
not
something that
equal.
doesn't exist is not equal to -5. So, but here's the thing: as I look at the limit of this function, when I want to check the limit from the left, this is to the left of 2, and so I can plug 2 into this piece and see what I get. What that's going to do is it's going to give me the value of, if there is one, a hole that I'm approaching from that side. Same thing on the right-hand side. Limit of g of x approaches 2 from the right is really about me finding which section is to the right and evaluating it directly by plugging that same 2 right there and seeing what I get. So the limit does exist because from the left and from the right, we're both headed towards -1. It's just that at 2, it's -5. So there's like we're going, so here we are, here's 2, we're going towards -1 from here. We're going, so what we got? We got x plus x minus 3. So we have like that from the left. We've got a 3x minus 7 from the right. But there's a point right there. That's kind of what that graph looks like. From the left, we've got this x minus 3 line. From the right, we've got this 3x minus 7 line. But right at 2, there's a -5. So it's definitely defined because there's a spot at 2. It's not that the limit doesn't exist. How do I know? I just plug it into the top one and the bottom one and compare those results. So that limit does exist. It's just that they're not the same. That's why this is not continuous at x equals 2. So no big surprise that a possible answer like D is there. And when I see that, like, so B is an answer, C could be an answer, and D says B and C, that probably means one of those is right. Now, maybe both, but definitely one of them. So, but then like E is all of them. Oh, geez, I better go back and check all of them. So like looking at the kind of multiple choice options kind of led me to the feeling that I'm not necessarily looking for the right answer. I'm looking for which ones to get rid of. So that's what I did first. I said, no, definitely defined. So A, and as soon as I did that, A and E are both gone. So if A is not true, then E can't be true. So now it really just comes down to, well, is it both of them or is it just one or the other? And so with dealing with those piecewise limits, checking from the left is checking one piece, from the right is checking the other, and then you compare those. Yeah.
The practice that we're doing on Wednesday, is it more practice or?
Yes, lots and lots and lots of practice. And so what I'm going to do is I'm going to start sectioning them off into the kinds of things, like, because I know a lot of our practice has been kind of all over the place. What I want to do is I want to do like, okay, here's like a bunch of graph practices. Here's a bunch of table practices. Here's a bunch of rationalizing practice. Here's a bunch of factoring practice. And kind of like focus you in on the handful or two of ideas so you can practice them over and over again. And like, okay, I've got like, there's 5 graphs. I got to the 3rd one. I definitely get it. Now I can stop. Here's a bunch of factoring practice. Okay, I did 8 of them out of the 15. I don't know how many I'm going to make, but okay, that's enough. Now I get it. So you can kind of figure out how much of each kind of practice you think you need to do. That's my plan. Yeah. Let's see if I can do that in a night. But I'll include like the kind of like practice quizzes and practice tests that they have. Like this is part of that, this multiple choice practice. So I'll make copies of a lot of stuff, I think, over the next 24 hours. There you go. I will finish this up and put it up on Canvas as part of the solutions for chapter 1. Other than that, we are good to go. Again, so stop.